Okay, welcome back for video C9, Find the Familiar Problem. So our learning goal today in this video is going to be I can pause before solving and look for familiar structure inside an unfamiliar problem. A little more specifically, in trig, I can reduce unfamiliar angles to familiar reference angles and quadrant signs. So you can see the little tagline there is just every difficult problem has a familiar one hiding inside. And that's kind of the big idea here. Keeping it more general, that's our big idea with this video is like we know a lot of we've seen a lot of questions in math, so we have a big knowledge base for familiar questions. So strong mathematicians, they don't treat every problem as brand new, right? Very rarely are you solving a brand new problem. What we want to do is we want to pause and ask ourselves, what familiar structure is hiding inside of this unfamiliar looking problem? Reference angles are one application, so I will be doing one application of it, but this is a very holistic approach to problem solving, right? So we're trying to break down unfamiliar problems into smaller, familiar steps. So you can see our hook. You can see the big idea there, but we have x minus 4 squared equals 25. We then have x squared minus 16, and we have sine of 150. So I'm going to get you to pause, and you're kind of asking yourself, what familiar structure is inside of each problem? Now, one of those, if you've been watching this video series in order, you have seen, especially that first one. But again, just take a minute and pause and ask yourself, so what familiar structures are hiding inside of those potentially unfamiliar problems? Okay, so as always, let's go through, and we will be seeing these questions in the 3 I do's to follow. So let's start with I do 1. So I do 1, we have this pretty familiar looking question overall. X minus 4 squared equals 25. Now, we have done questions like this before, but this is a nice kind of comfortable launch point. So as we look at this, a couple things we're asking ourselves. So first of all, what is the outside structure? So as we look at the outside structure, we see it's a square, right? So we see we have something squared. So we have that kind of something squared. So what familiar problem does this remind us of? And it kind of reminds us of the square root equations, because I can see if I square root both sides, well, now I don't have that square anymore. And then finally, what would make this harder? And harder would probably be expanding this first, because if we expanded that perfect square, we have to pull the 25 over, try to solve it by factoring. That looks like a harder question. So as we look at this, our familiar structure is a square. Our method suggested then would just be a square root solution, right? We don't need to reinvent the wheel and expand and make this question harder than it needs to be. So now let's put that into practice here. So with this question, I'm going to say, well, okay, so x minus 4 squared equals 25. So what we're saying is let's follow the structure of the question given. Let's use that square and square root both sides. Now again, because we introduced a square root, we know it's going to be a plus or minus. So that's going to leave x minus 4 is plus or minus 5. So then if I add 4, I'm going to get x equals 4 plus or minus 5, which gives us 4 minus 5, which is negative 1, or 4 plus 5, which is 9. So our solutions are going to be negative 1 and 9. It's a quadratic, so I'm not worried about any domain restrictions there. And that's it. So that's the question. So the idea here, again, this was not a new problem. It was a familiar square root equation with x minus 4 in place where the x usually sits. Okay, let's move on to the next question. So the next one here is a factoring pattern. So as I look at this factoring pattern, I see x squared minus 16. So before expanding or doing random algebra, we're asking ourselves, like, what does this look like? Now, this is just kind of quadratic set with no context. So there are going to be contexts where we might just kind of do a quick step and finish the question. But as you look at this, we kind of see that difference of squares. So the difference of squares. So what do we notice about it? So what can we do with that? Can we rewrite 16 as a square? Yes, because 16 is equal to 4 squared. So we have that familiar pattern. We can utilize that in our question, right? So x squared minus 16, what we can do is we could say, well, okay, that's x. Let's put a middle step here. So this is equal to x squared minus 4 squared, and that's a perfect square. So x plus 4, x minus 4. And that's it. So yeah, that is our kind of like looking overall. Like these are very generic strategies, but our main kind of strategy is when a problem looks difficult, we want to pause and ask ourselves, what does this remind me of? Where have I seen this before? What familiar structure might be hiding? What's different this time? And then what do I need to check in that original problem? Right. So hopefully a question can boil down to, like we said, kind of a familiar question that we have seen before. So let's connect that with trig, an actual newer scale we're looking at. So sine of 150. So sine of 150, we want to evaluate that. Now we could use our unit circle, but let's try to move beyond the unit circle a little bit. 150 degrees is not one of our first special angles. So our question is going to be, what familiar angle is hiding inside? So to do that, I often recommend just sketching it, right? So for 150, I'm going to sketch what a 150 degree angle looks like. Again, I know 90 degrees is here, 180 is here, 270 is here, and then 0 or 360 is here. So 150, we can see, well, okay, it's between 90 and 180. It's in there. So 150 looks like that. So I can see 150 terminates in quadrant 2. So quadrant 2. Then let's go after the reference angle. Well, the reference angle, we can kind of see here. The reference angle is going to be, what's the distance back to that axis? So if I look at that picture, I'm going to say, well, 180 degrees is all the way back to the axis. I've turned 150 degrees, so the remainder there is going to be 30 degrees for the reference angle. So my reference angle is 30 degrees. So that's our familiar angle. 30 degrees is familiar because we know what sine of 30 is, sorry. So we know sine of 30, we know that's from our special triangles. Sine of 30 is 1/2. I then use my quadrant information. So because I'm in quadrant 2, I know that sine is positive because the y values are positive over here. So what that tells me is I know it's 30 degrees, I know it's positive. So therefore sine of 150 is going to be equal to sine 30. And I know sine 30, so sine 150 is going to be positive 1/2. I can put that up here as well. So sine 150 is equal to 1/2. So again, that's a nice example where sine of 150, maybe we couldn't directly evaluate that if we didn't have a unit circle on us. But what we can do is use a reference angle, and that is a familiar question on that one. So yeah, the big thing to note there again is the triangle gave the size, the quadrant gives the sign. So let's move on to a you-do question. So you-do, here we go. So I want you to try a familiar question with cos of 210. So cos 210, you're pausing the video here and asking yourselves again, so what familiar angle is hiding inside? Try it by first finding the reference angle and then using the quadrant information to decide the sign. Okay, so I had poked that up there before, so you can see it is going to be negative cos 30. Because so 210 is in that quadrant 3, which tells us that cosine is negative in quadrant 3. We also have a reference angle again of 30, so 30 degrees back to the axis. So what we're saying is our familiar angle is that 30 degrees. We know cos 30 is root 3 over 2, so cos 210 is just going to be the negative sign of that because I'm in quadrant 3. So again, back to that familiar line, that triangle gives us the size, the reference angle tells us the size of the ratio, and the quadrant tells us the sign of the ratio. That's it. So let's look at one more. And this next one is just an overall question. So you see 3 problems. So absolute value of x minus 2 equals 7, square root of x squared minus 9, and a question about the domain, and then 2 sine theta minus 1 equals 0. So question for you is, what does each problem remind you of? Don't solve them. You're just kind of identifying the structure here. So pause, try that question. So just name the familiar problem hiding inside each one. Okay, so looking at the 3 here. So if we look at that first, the absolute value x minus 2 equals 7. Well, this is really a root corner question because we know absolute value will never be negative. Wherever it equals 0 is kind of our corner point. So what we would do with that question is we would find that root to give the corner, and then we would split into 2 cases. Kind of say the case we said where it's positive, it's normal, and the flipped over version, the kind of reflection piece. And then we would solve it. For the middle question, again, really similar structure. So x squared minus 9 under a square root. Well, we know the x squared minus 9 will have roots. Those roots will be boundaries. And then we know we would only want to pick the positive piece. So very similar to the absolute value question. Again, you're going to find the roots. The roots act as boundaries. For the absolute value, they become the corner points. For the quadratic, underneath the radical, they become domain restrictions, bounds. And then finally, that trig question looks big, but if you isolate the sine theta with just simple algebra, you get sine theta equals 1/2, which then becomes a reference angle unit circle question. So again, not solving them, but kind of identifying those familiar structures within potentially unfamiliar questions. So our final checklist here, is going to be find the familiar problem. So our question is again asking ourselves, what does this remind me of? So again, just kind of going back to the start. So the strong mathematicians, we don't memorize thousands of separate problems. What we want to recognize is familiar structures hiding inside of those unfamiliar ones. So just like chess players recognize patterns, musicians recognize chords, mathematicians recognize structure. So once you recognize that structure, what a name is it a square, factor pattern, boundary, triangle, identity, equation type? What is it? And then identify what's different this time. So maybe we have a sign flip, a little shift, a restriction, a quadrant, some context. There's probably something different about the question if you're thinking about it at this level. Use that familiar method. So whatever structure you identified, we'll have a kind of method to go along with it, and then adjust for the new detail, right? So like above, x squared minus 9, I can find the roots, and then I realize, well, this is a radicand, it's underneath the radicals, so I'm going to use those roots as boundaries. And then make sure, again, you are checking the answer in the original question, right? So make sure everything does kind of line up for yourself. And that's it. Thanks for watching, and I'll see you next time.